So hi guys. Mm, We will be today discussing about the revolution which self-supervised learning has brought in computer vision in recent years. I am Muskaan and I am currently working as a computer vision engineer in Singapore, and I worked as a researcher at EIS Lab Sweden. So let's hop into the table of contents for today. We will be first covering the basics of self-supervised learning, the idea that why we need self-supervised learning and why the existing techniques were not enough for computer vision. Then I will give you a brief overview of subtypes of SSL and different types of SSL and its subdomains. Then we will be focusing on Dino V2, which was the recent SSL model proposed by Meta AI, its loss functions and the benefits, that what benefits we get when we use Dino over other models. We will end this with applications of Dino. So I hope that everyone here is aware of basic machine learning techniques like supervised, unsupervised, and reinforcement. If not, I can give a brief overview. So supervised learning is the most common type of machine learning which is used. It uses a data set with labels. This means that each data point will be given a label for the training process, and the goal is to train a model which can predict the output of new data points. For example, if you have a data set of images of cats and dogs, you can use supervised learning to train a model that can predict whether the image is a dog or a cat. Unsupervised learning, on the other hand, is used when you do not have labeled data. It gives you clusters or it helps you to find patterns between the data set. Reinforcement learning is a type of learning which is based on agent learning by the environment. The agent interacts with the environment and receives the rewards or punishments depending on it. This is the most basic techniques which robots use to train themselves. If anyone has any question, please feel free to ask during the session. So my question is that how can we solve the problem of using large amount of labeled data as in supervised learning till date? For every domain like healthcare and satellite imagery, there is not enough data available to evaluate our data sets and inputs to get a good industrial kind of result. So self-supervised learning comes to a role here, which solves the problem of using large amount of labeled data. So basics of SSL, we will go through first. If anyone has any idea or any hint that what is SSL, I would love to hear. If anyone can unmute and tell.
SSL map is a basic technique in machine learning and deep learning, which is self-supervised learning, and it works on the data which does not provide, which we do not provide labels. That is the no unlabeled data, the totally unlabeled data.
Yes, that is correct. In traditional supervised learning, we largely rely on high label data. However, this approach can be limiting because it requires a large amount of labels, which is not possible in computer vision. We do not every time have medical image classified in correct classes, or we do not have resources to get them correctly classified for training purposes. So SSL offers a promising alternative by leveraging the unlabeled data to learn useful representations or embeddings that can then be applied to downstream tasks such as classification or segmentation. It offers a promising alternative as well because we can use the plenty of unlabeled data which is available in the world, and we can use it for object detection, localization, segmentation, and classification. It has also been gaining traction in recent years due to its potential to reduce reliance on expensive labeled data and improve model performance. By understanding the fundamentals of SSL, you will be better equipped to stay ahead of the curve of rapidly evolving world of deep learning. So types of SSL. There are four major types of self-supervised learning categories available. The first one is contrastive learning. Second is information maximization. Third is knowledge distillation. And the fourth one is clustering. So briefing over one by one, contrastive learning has three major categories or three major models or architectures, that is SimCLR, Perl, and MoCo. Redundancy reduction, on the other hand, includes Barlow twins and Vickers. Then self-supervised learning has distillation, which has Buell and Dino. Clustering, on the other hand, includes deep cluster, Sela, and SWAR. Contrastive learning involves training a model to differentiate between similar and dissimilar pairs of data points. The process involves creating two versions of same image and then training the model to identify whether they belong to same or different classes. By doing this, they learn to learn to extract the meaningful features from the data which can be used for downstream tasks. One advantage of contrastive learning over supervised learning is that it does not require labeled data in large amounts because it is expensive as well as time consuming to generate. Additionally, contrastive learning can help improve the performance of models in low data regimes where there may not be enough labeled data. For example, the cases of diabetic retinopathy, satellite imagery, breast cancer, or histopathology cases, etc. Next is information maximization. This is an interesting approach to self-supervised learning. It involves maximizing the mutual information between the set of input variables or images and the set of output variables. It can be further used to learn the useful representation without the use of labels. Only the things which are used are input variables and output variables and the maximization of information between them. Now, why do we maximize the information? The maximization of information leads to identification of patterns and relationships within the data that would be otherwise difficult. This approach has been applied successfully to natural language processing before, and now it is showing promising results on computer vision tasks as well. Next is knowledge distillation. Knowledge distillation is a process of transferring from a large complex model that may be referred to as a teacher to a simpler model, the student. A smaller, more lightweight model is trained to mimic the behavior of the teacher model or the larger model. This can be done by training the student to copy the predictions of the teacher or by training the student to predict the teacher's soft labels or weak labels. This technique is also referred to teacher-student model, using a teacher model that has been pre-trained on a large data set of unlabeled data. If we talk about NLP, that is ChatGPT, which has been pre-trained on large amounts of data, it can be considered as a teacher model for a smaller downstream NLP dataset. The student model is then trained to mimic the predictions of the teacher model. This helps the student model to learn the feature representations better and leads to improved performance on downstream tasks. Last one is clustering. So clustering is also done in unsupervised techniques, but in self-supervised learning, it is used to learn the meaningful representations without any label data. Clustering is an unsupervised method, as I said before, but in SSL, it can be used as first training a feature extractor in first step and then predicting the relative position of image patches or the order of frames in a video. Clustering methods can be used for a variety of tasks such as classification, object detection, semantic segmentation, etc. Now, Our main topic for today is Dino V2, that is kind of SSL model recently proposed by Meta AI. All over there was buzz on every social media platform when it was launched. So it is basically proposed to scale the levels of SSL that are currently being used. It is a self-supervised model which was developed by Meta AI recently, and it is able to learn from unlabeled data and achieve state-of-the-art performance on a variety of tasks such as segmentation specifically and classification as well. It works using a teacher-student framework. The teacher network is a pre-trained model that has been trained on a large data set of labeled images. Self-supervised learning basically is a two-step process. First is pre-training and second is downstream tasks. In pre-training, we use the self-supervised learning architecture to learn from unlabeled data and generate a set of embeddings which can be used in downstream tasks. Then in downstream, we use a logistic regressor for different percentages of training data to compare the results. And in self-supervised learning, using the pretext checkpoint, which was trained on unlabeled data, we can get even good results which are close to 100% labeled data on 1% and 10% data as well. So the student network is trained to predict the output of the teacher network given the same input image. The process of distillation helps the student network to learn more robust and generalizable features. Dino V2 also uses a number of other techniques to improve the performance of the student network, such as local to global correspondence. This technique encourages the student network to learn interpolate context from a small crop of an image. Center and sharpening. These techniques help to prevent the student network from collapsing into a single mode. And contrastive learning. These help the student network to learn distinguish between different type of images. Either they are similar or dissimilar based on the contrast between them. So here's the new data pipeline which was introduced in Dino V2. Dino V2 builds a huge dataset by curating existing datasets, which makes it easier for Dino to train on large datasets as compared to its previous version. Data processing pipeline, which is the main contribution of this paper. The aim of this pipeline was to get quality training dataset at large scale. This figure is from the Dino V2 paper released by Meta AI. And there are two sources of data. One is uncurated and one is curated. The source tasks are classified are classification, fine grain classification, depth estimation, image segmentation. The uncurated dataset can be gathered by the meta tags of image from web crawling, and approximately 1.3 billion images. As the first step, these uncurated law deduplication process images go through a deduplication process using what is called a copy detection pipeline, which is based in this paper. SSL descriptor for image copy detection, which in turn is built on top of SimCLR and removes duplication by detecting similar and unsimilar images through its architecture and laws. The main focus of this pipeline to use multiple data sets existing and curate a larger data set at scale to improve the computer vision task. The Dino V2 architecture focuses on pseudo label generation and then transfers the knowledge by matching the probability distribution. It uses officially the activation functions such as softmax, centering as discussed before. The teacher model goes through centering and softmax and a probability distribution is generated. This knowledge is then transferred and matches the probability distribution by the second student model. And this probability distribution after matching is transferred to the downstream task. Some mathematics behind the Dino V2 is its loss function, which plays a very important role. The loss function majorly comprises of two terms, that is, as you can see, Zi and Zj represent the two patches of images that are close together in space. Here, Zk is a patch of an image that is far away from Zi in space. The latent space or the image space is generated after the images are augmented and they pass through the architecture. The probability of Zj and Zj come from the same image. This probability is such that Zi and Zj are the patches of the same image, and Zi and Zk probability is such that Zi and Zk come from different images so that it can differentiate and the probability distribution can be matched correctly. The first term in the loss function is a cross entropy loss, and the second term in the loss function is a log likelihood loss. The loss function is defined to encourage the student network to learn the features that are discriminative of the image. It is also optimized using SGD or stochastic gradient descent. The patches are sampled randomly from the training dataset, and the student network is updated to minimize the loss function, which had two terms as discussed. So why we upgraded from Dino V2, why Dino V1 was not enough? One major reason was the scaling of data and self-supervised learning. It was not currently feasible with other architectures. It performs better. Dino V2 has been shown to achieve state-of-the-art performance on variety of tasks such as computer vision, image classification, segmentation detection, localization. It has more effective training as well. Dino V2 can be trained more efficiently than other SSL model because it has a teacher-student framework. It is more robust to noise. Dino V2 uses contrastive learning, that's why it is more robust to noise than other SSL models. It has more flexibility as well because it can be used to use for variety of applications as we already discussed: segmentation, detection, localization, classification. Some major differences which we need to point out between Dino and Dino V2 are data. MetaDino was only trained on ImageNet, which has approximately 1 million images, while Dino V2 was trained on larger dataset. Images were curated from a smaller dataset, and it was approximately 1.3 billion. This allows Dino V2 to learn more robust and generalizable features. Model architecture as well. Metadino uses a ResNet 50 architecture, which is a very generalized architecture these days, while Dino V2 uses a Vision Transformer VIT architecture. These architectures are more powerful than ResNet architectures, and it allows Dino to perform better. VIT or Vision Transformers work by breaking down images into series of patches, which are then embedded into sequence of vectors. These vectors are then passed through a transformer encoder, which learn to identify the relationship between different patches in the same image. Training procedure is also different or upgraded as compared to Dino. Dino was trained using a contrastive loss, while Dino V2 was trained using a more sophisticated loss function called the InfoNCE loss. The InfoNCE loss is better to encourage the model to learn the distinguished features and also allow to achieve better performance on the downstream tasks such as segmentation, classification, etc. Performance Dino V2, as I already said, achieved state-of-the-art performance results on majority of computer vision tasks and datasets. So Dino previously was not competitive on these tasks. Application of Dino V2. How Dino V2 can be applied in real life. So it can be used to train classifiers that can identify objects in images. This can be used for variety of tasks such as facial recognition, biometrics, object detection, and image search on search engines. Dino V2 can be used to train object detectors that can identify and localize the objects in images. This could be used for a variety of tasks such as self-driving cars, autonomous objects, video surveillance, and medical image analysis. This could be used for a variety of further applications such as satellite imagery and rooftop analysis for solar panels. It also can help with visual question answering. It comes under NLP in a way. Dino V2 can be used to train visual question answering models and answer questions about the images. This could be used for a variety of tasks such as tutoring, customer service, and search. And yes, that's it for Dino. If anyone has any questions,